Welcome to Nano Matters, the podcast that explores examples of nanotechnology. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Here with me today is Jim Schuck, Associate Professor of Mechanical Engineering at Columbia University. So Jim, why does being able to image details at the nanoscale matter, and why is it hard?
Both good questions. It matters because most of what determines a material's properties are determined by what happens at length scales on the order of about 10 nanometers. That's sort of the whole origin of nanoscience. We're kind of trying to take advantage of that fact that properties can be changed by manipulating what happens in materials at that length scale. The issue is that many people are familiar with optical microscopy, right? If you want to characterize the material at that length scale, it gets hard. You need to have high resolution techniques. And so some of these techniques, these have been developed just, in the past few decades, include things like atomic force microscopy, scanning tunneling microscopy, right? These scan probe techniques. X-ray imaging, right, has been around a while. People know that can give high resolution imaging. The issue is all of those techniques tend to be, particularly the scan probe techniques, the electron techniques, tend to be very good at giving you high resolution. They're less good at telling you about the material properties. And meanwhile, optical microscopy tends to be good at giving you sort of chemical properties, giving you material properties, but is not very good at giving you the high spatial resolution. And that has to do with the fact that there's a diffraction limit. If you have two objects separated by distance smaller than half the wavelength of the light that you're shining on it, you won't resolve them. They'll just look like a big blob. And if your interest is in investigating nanomaterials or nanostructured materials, that turns out to be a big problem. And yet you still have these advantages of optics and optical spectroscopy and microscopy that you'd like to apply to these materials. That's kind of, in a nutshell, driven what we've been working on.
So can you tell us about the technique that you and your team have developed and you're able to actually image at the nanoscale?
Absolutely. So I would say we actually use two techniques, but I'll probably then concentrate more on one. One is, even if we're using diffraction-limited optics, as we call it, right? They can't see two objects that are closer than a few hundred nanometers together. We can use small objects as reporters, things like fluorescent molecules. So the idea is that it turns out that lots of fluorescent molecules and some other types of luminescent objects are very good reporters of their local environment. And so if you can see a single molecule, and if it changes its color or turns on and off, depending on if the pH changes in a material or the pressure or the temperature, then you know that the molecule is only sensitive to what's happening in its nearby environment. It can tell you about what's going on at those length scales, even if when you actually take an image of that molecule, it looks much bigger. So one is kind of somewhat indirect, to use the local reporters to tell you about environments. Another way that we think of as maybe being a more brute force way of beating the so-called diffraction limit is to take our light. We've spent a lot of time figuring out how to engineer antennas for light that capture optical fields and then concentrate that energy down to sort of the nanoscale. And there's all sorts of fun antennas. We and many other people in the optics field now make variations of these types of antennas. They have fun names like horn antennas and bow tie antennas, things like that. And you imagine something that we, early on studied a lot of were these bow tie antennas, which are like two nanoscale metallic triangles that face each other tip to tip. They look like a bow tie. But there's a tiny little gap between the two tips. And when you make these tiny gaps, it turns out that under the right circumstances, your antenna will capture almost all of the energy in sort of a light field or light spot and focus it down into that tiny little gap. Then once you have a tiny little spot of light, right, it's like a nanoscale light bulb or a little nano laser, that then you can drive it around and use it to probe optically dimensions on the 10 nanometer length scale.
So what types of discoveries or information have you been able to uncover by using these antennas?
Oh my gosh, this is part of the fun, right? Because we're looking at these length scales that you can't see with normal microscopes, often what we see is almost everything is new and surprising. We spent a fair amount of time studying what I'd say lower dimensional materials. These include 0D materials like quantum dots and 1D materials like nanowires, and then 2-dimensional materials, 2D semiconductors in particular. These are like flat sheets that are sort of atomically thin. We had recently been very interested in these 2D semiconductors. They're of interest for lots of reasons, but in particular, you might imagine that if you have truly atomically thin semiconductors, you can make maybe very efficient, very small electronics and electronic and photonic components that use less energy because they have very small footprints. So we were interested in investigating their properties. One of the things that we discovered in these materials was that There are various ways of getting these 2D materials. The most common way is, and the way that sort of was discovered, is you find a larger crystal of the material and then you exfoliate it. You basically rub it against a piece of tape or a piece of paper or a glass slide, and some layers come off, and then you search around and find one that's one layer thick. As you might guess, if you're trying to scale up to use the material for making electronics, that's not particularly useful. So what you need is, there's whole efforts in people figuring out how to synthetically grow these two-dimensional semiconductors, like at wafer scale. And one of the first things we showed is that when you go in and look at it, all of the synthetic material that's grown, in the process, all of the material around the edges of all synthetically grown 2D semiconductors has sort of this quasi-amorphous, actually more like polycrystalline region that exists at the edge. And that turned out to be really important because until then, people would try to do things like, well, you want to put electrical contacts onto your material. And so people would look at basically the same material that came from the same lab, and they get just dramatically different results about how the material behaved electronically. And you realize, oh, well, that's because these people were putting their contacts at the edge, some were putting it more in the center. And so just realizing, for example, that there's this sort of nanoscopic polycrystalline regime that exists in all of these synthetic materials was one thing that turned out to be rather useful. We've also been able to reveal the origins of so-called single photon emitters, or some of the single photon emitters that exist inside these 2D materials. That's useful because when you have a single photon emitter, well, there are a number of things you'd like to do with it, including tuning its properties, its frequencies, its colors in particular, its wavelengths. But you can't really do that until you understand what the single photon emitter is. And so we've had some luck showing that actually very localized strain can itself lead to the creation of these quantum dot-like states that give you single photons in these materials. So again, they have to happen very locally. They originate from things that we call nanobubbles and nanowrinkles. Actually, it was by looking within a single nanobubble and seeing regions that nanowrinkled that we could understand how strain could be the origin of these emitters.
This imaging technique that has enabled you to uncover some of these variations in 2D materials that perhaps were unexpected when you started your examination is clearly one area where you've impacted our understanding. Where do you see this technique's application in the future? I mean, what problems are you hoping to solve or understand better using this imaging technique?
There are a couple things. So first, actually, I'm going to take a step back. One main challenge of the technique has been, I'd mentioned the optical antennas earlier, has been figuring out how to get good optical antennas at the end of scan probes. So we'd mentioned briefly atomic force microscopes before, but these are, sharp tips that drive around and kind of drag along the surface of a material. In order for us to turn that into an optical microscope, we have to put an antenna right at the apex of the tip that's touching the material. And so that turned out to be like a 5-year fabrication challenge. And so working with colleagues at the Molecular Foundry and their nanofabrication facility was critical to being able to figure that out. But one thing that we learned was, well, both how difficult but also how important it is to be able to place nanoscale objects in desired places. So one thing that our technique continues to allow us to do is to go in and study materials where people in nanoscience are trying to position various structures on a substrate or build up more hierarchical type structures out of nano building blocks. How do you know if you've put them in the right place and if what is in the right place is the material you wanted? Certain techniques like electron microscopy are very good at telling you can see if things are where you want them, but you don't know what it is that's there. So the optical spectroscopy helps out on that front. Okay, so what do we hope to see? So we would like to then study materials where they've been trying to make more complex structures using these nanoscale materials and building blocks. We mentioned the single photon emitters. What you really want if you're trying to do quantum optics or quantum information processing, you want to deterministically position these emitters and place them in ways that they can interact with each other. So they need to be close to each other. They don't have to be, but there are good reasons. If you're trying to make a quantum circuit, you'd like it to be as small as possible. So we would like to go in and study these types of systems where really there's not a good way to go in and probe the one single photon emitter one by one, except using techniques like this. If these emitters are separated by 10 or 20 nanometers from each other, if you shine a regular laser through a regular microscope onto these subjects, you excite them all at the same time. So we get this ability to go in and individually address lots of individual components. So that's something that we're excited about, is building up these networks. We can actually use our tools. You've probably heard of optical trapping, we can use things like optical forces associated with our little nanoscale optical spots to induce strains or temperatures to perhaps create some of these types of sources. And then we can go in and probe their properties one by one and learn about how they work. So that is one direction that we're going in.
Well, that sounds very exciting. And I remember the early days of atomic probe microscopy, and it's exciting to see how many properties we can now probe. And the fact that you're coupling it with your antennas to be able to image where you want to, I think is really exciting.
It is. You're exactly right. And the neat thing is, each one of these techniques and new tools gives you a new piece of information. And then the real power is then correlating that with the other tools that are also out there, right? And that's when you kind of get a more complete picture about sort of the new materials and new properties and new devices that are being developed.
So, Jim, I want to thank you for taking the time to talk with us today. Do you have any closing thoughts that you'd like to share with our listeners?
I think my only closing thought would be, don't be afraid of the gray goo. I teach a nano course. It comes up every course, and for good reason, right? One of the main points is to create structures, materials, devices that have properties that otherwise it didn't exist before. And so whenever you're making materials with new properties, you have to think about what these properties can do, what they can be used for. You have to be cognizant about safety, right? And I guess I would say, so I think there's sometimes the worry that people don't think about those things. Absolutely, of course, new properties can always be abused, and so that's something that people need to consider. But at the same time, I think that nanoscientists take that seriously. It's both a worthwhile question to ask about, but I also spend a lot of time convincing people that nanoscience is worth it.